Hello, so we're here talking about men in well diagrams. So we learned about Bohr, and so the Bohr model of the atom says that our electrons exist at different energy levels around the nucleus. Now, a men in well diagram is just a way to help us continue to visualize what that means and what it means for these properties of these electrons and these atoms. And so it is based on the Bohr model. You're going to notice some similarities between this and Bohr model drawings. But again, it's just another tool for us to help understand what's going on at the subatomic particle level, since we can't really see it with our own eyes. So let's take a look at this ionization energy graph. So this is based on photospectroscopy, which tells us about the relative energies of electrons around an atom. So ionization energy in particular is telling us the amount of energy it takes to pluck off an electron from an atom. So we know we've got the positive nucleus and we've got the negative electrons. So that positive nucleus is pulling the electrons in. We've got that attraction. Think about two magnets. And it takes energy to pluck that electron off, to pull it away from the positive nucleus. So if we look at helium here, you can see helium, two protons, so it's got two electrons. Each dot represents an electron being plucked off. To the right, so think about it opposite the way you read a book. So this first electron is being pulled off. Well, I guess it is. It's the same way you read a book. Never mind. So this first electron here is being pulled off. It takes less energy. The second electron here takes more energy to pull off. So it takes less energy to pull off the first one, more energy to pull off the second one. Let's take a look at why. I'm going to use this idea of a men in well diagram. So it's like we have this well. And down on the bottom of the well, I'm going to put the 2 plus charge of helium. The positive charge is what determines the depth of the well. So a bigger positive charge from the nucleus, it's going to be a deeper well. It's going to take more energy to pull those electrons off because it's a stronger attraction. So it's like I've got two guys in the bottom of the well. Well, if I've got two people, one of them can get a boost from the other. It's like he could stand on his shoulders. That's how the electrons act. So if I've got that positive 2 charge divided between two electrons, it'll be a little easier to pluck the first one off. But then once this first one is gone, the second guy, it's positive 2 charge in the nucleus versus 1 electron. So that attraction's stronger. It's going to be harder to pull that second one off. So it's like when there's more electrons, they get what's called a shielding effect. So the other electrons help disperse that attraction from the nucleus. So it makes it a little easier to pull them off. And then so every electron you pull off, that just means the nucleus gets to pull a little stronger on the ones left. So it's a little harder to pull them off. Now lithium, you'll notice I've got these two here. Then this guy is a little lonely. He's kind of off. There's a break. And we're going to see that break a little more obviously on the next one. So the break is not super obvious in this graph, but it's going to be really obvious in the next few. So lithium, 3 plus charge. Notice how I'm at 120 to pull off that last electron versus I was only at 50 to pull off the last electron here. So my well is deeper. It's taking more energy to pull off the electrons. I still got these two guys in the bottom, but this first electron looks easier to pull off. Like it's really easy to pull off. See how it's almost zero? It's almost like that one is on a ledge. Or you might think of that as a Bohr model, different energy level. So we've got a new energy level. It's like a ledge. So that one's going to be a lot easier to pull off because it's further from the nucleus. If I have two magnets and they're far apart, you don't feel a very strong attraction. But if I put them close together, they snap together. You feel that attraction. So distance matters. So let's scroll down. Okay. So you can see this gap. It's a little more obvious. So this is the bottom of your well, and then this is the ledge. So here we've got 2 electrons on the ledge, 3 electrons on the ledge. Let's keep looking. 4 electrons, 5 electrons on the ledge, 6 electrons on the ledge, 7 electrons on the ledge. Notice how my well is getting deeper as I go across. So we'll just stop and draw a men in well really quick. This one's going all the way down to 1,000 because I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. That means I must have 8 protons. I've got I'm just going to draw heads here. I've got 2 in the bottom of the well, and then I've got 6 on the ledge there. Versus fluorine, notice my well gets even deeper. So as I add protons, my well is getting deeper. 3, 4, 5, 6, 7. Got neon. And then check what happens when I get to sodium and magnesium. There's another gap. So another gap. So that means there's another ledge. So that super deep well, 11 plus charge. I got 2 in the bottom. I've got 8. And then I've got a new ledge and 1 up there. So again, whenever we have this little separation, that tells us we've hit a new energy level, or in our well diagram, a new ledge. Helps us see distance matters. So we have shielding and we have distance that's affecting the energy it takes to pull off an electron. And if you look at your periodic table, you'll notice sodium starts a new row. The last time we saw a jump, that was at lithium. Lithium starts a new row on your periodic table. So that means when we hit the next row, which starts with potassium, we're going to get a new ledge. So at potassium, we're going to add another ledge. So we had a ledge at lithium, we had a ledge at sodium, we had a ledge at potassium. So every time we go down a row on the periodic table, we're adding another energy level or another ledge. The periodic table is arranged that way for a reason. So with that, you should be able to draw your own Menin well diagrams for the first 20 elements.